Welcome to Online Precalculus. Today, we're going to cover section 1.2, Basics of Functions and Their Graphs. Our objectives for this section are to first find the domain and range of a relation and talk a little bit about what a relation is and how it can and how you can use it to represent data. Then we'll determine whether a relation is a function. Then, just by looking at the data, then we'll determine whether an equation represents a function. Then we'll evaluate some functions. Then we'll graph some functions. And then we'll use a vertical line test to identify functions from their graphs and obtain other information about a function from its graph. Then we'll identify the domain and range of a function by looking at a picture, by looking at the graph. And finally, we'll talk about the x-intercepts and the y-intercepts of a function. So let's start our talk with relations. And the first relation is a little silly here. And this is a little old, as you can see. This graph represents the highest paid TV celebrities between June 2010 and June 2011. So when you're looking at this graph here, you might notice a few things. First, you notice that it has pictures on it. Okay, that's fine, whatever. Next, you might notice that Oprah Winfrey is the highest paid TV celebrity for this year. Okay, you might notice that the other people, made a decent amount of money as well. But the thing you really want to notice is that the two data points, right, the x-axis and the y-axis, are not both numbers, right? The x-axis is filled with people's names, the celebrity names. The y-axis has the earnings. So the y-axis is numbers, but my x-axis is filled with just people, okay? This is a relation. A relation is any set of data. So the graph indicates this correspondence between TV celebrities and a person's earning in millions of dollars. And you can see that we can make a set out of this by putting the braces on the edge there and just making ordered pairs with the person's name, comma, how much money they made. Okay, and these, now that we made a set out of these data points, we have made a relation. So the mathematical term for a set of ordered pairs is called a relation. And a relation is any set of ordered pairs. Could be people's names, could be numbers, doesn't matter. Okay? The set of all the first components in the ordered pairs is called the domain. So typically we think of domain as the x variables, which is true in this case, right? Because those are the people that were on the x-axis of my graph above. But it doesn't have to always be that. It could just be, it could be a letter, it could be a number, it could be a shape, a color, whatever. If you have ordered pairs, the first thing in the ordered pair is called the domain, and the second component of the ordered pair is called the range. Okay, and most of the time we're going to be using numbers to, to display the domain and range, but it doesn't have to be, especially not with this example. So if we have our relation here from the picture in the front, if we want to find the domain and range, the domain is all of the first components, okay? So that's Winfrey, Cowell, McGraw, DeGeneres, and Seacrest. Okay, all of the first components of the ordered pair. The range is all of the second components in an ordered pair. Okay. Now, good habit to get into. Right? I didn't do it in the first line because they were just names, but a good habit to get into with domain and range is to put them in order. So let's put the range in order. So we have 51, 55, we have 80 twice. So I don't have to write it twice, I only have to write it once. And then 315. Okay? So that is my domain, and that is my range of this relation. Let's look at another. Okay? So the domain, now this relation is just numbers. Okay? And we'll come back to what these numbers mean in a second. So the domain of this relation is the first coordinates, 0, 10, 20, 30, and 40. And the range is the second coordinate. And let's try to get them in order here. We have 6.7, 9.1, 10.7, 13.2, and 21.2. Okay. So again, we don't know what these numbers mean yet. We'll find out on the next page. But the domain is the first coordinate of an ordered pair, and the range is all the second coordinates on an ordered pair. Okay. So in that checkpoint, did you wonder if there was a rule that assigned the inputs to the outputs? So y was 30 associated with 13.2, in the weird that the textbook picked out the fourth term, not the first, not the second. Well, if you look at these two graphs, you can kind of figure out where these numbers came from. Okay, so if you look at the bar graph on the left, we have the percentage of first-year United States college students claiming no religious affiliations. The green is women, the orange is men. And you can see these numbers for women should have looked a little familiar from the previous page. And in fact, if we change the scale on the bottom from just strictly years, like we have right here, to years after 1970, we now can get the 5 ordered pairs that we graphed in our checkpoint. 0, 9.1, and 10, 20, 30, and 40 with my different output, my different percentages. Okay. And you can see that we changed this data from the bar graph on the left to these ordered pairs with years after 1970 and percentage of first-year college women claiming no religious affiliation. And that is where the input 30 and the output 13.2, this guy right there, that's where those ones came from. Okay, 30 years after 1970, 13.2%. Okay, so we represented this data with a bar graph that was a little cluttered on the left right there, and with data points on a graph in this right. Another way we can use to represent this data, to visually represent the data, is with a mapping diagram like we have down here. A mapping diagram is just a way to say which numbers in the domain go with which numbers in the range. Okay? So let's use these mapping diagrams and talk a little bit about something called a function. Let's go back to the celebrities and how much they get paid. Okay. So if we look at these correspondences with these mapping diagrams, you can see in the one on the left that every person makes one amount of money. Yes, Simon Cowell and Phil McGraw make the same amount of money, $80 million, but every person makes one amount of money. As opposed to this mapping diagram right here, if we reverse it, you can see that if I asked you, well, who makes $80 million, you couldn't really tell me because 80 goes to 2 different places. Okay, so both of these are relations, but a relation where each member of the domain corresponds to exactly one member of the range is called a function. The one on the left is a function. The one on the right is not a function because 80 goes to two different people. Okay, so that's what this says right here, that it is not, the second one is not a function because of these two data points that the x value repeats. Okay, a function is a relation in which no two ordered pairs have the same first component. Okay, unlike 80 Cowell, 80 McGraw. So same first component, different second component. It is not a function. So here's our formal definition for function: is a correspondence from a first set called the domain to a second set called the range, such that each element in the domain corresponds to exactly one element in the range. Now, like in the first one on the left side here, these two correspond to one number. They're both the same number, but that doesn't matter as long as all of the inputs correspond to one output. Back to our college example, you can see that every input is different. Okay, years after 1970 makes sense, right? They're all going to be a different number. So because all the x values are different, this illustrates a function. Okay? So let's determine whether each of these relations is a function. And if we look at A, every x value is different. So yes, that is a function. For part B, those two are the same input, different outputs. No, that is not a function. It's still a relation, still data. We can still graph it, we can still manipulate it, we can still do whatever we need to do with it, but it's just not a function. Let's try our checkpoint. So when we look at these very carefully, focus on the x coordinates. So that is not a function. And this one, as we double check all four, yes, that one is a function. Okay, so that's how we can tell if we have a function when we're looking at raw data, right? If we're just looking at the data points, okay? You can also tell whether or not we have a function if we are looking at the equation, okay? So functions are usually given in terms of equations rather than ordered pairs. That's pretty normal. The equation for the first year college women was listed right there. Y is equal to 0.014x squared minus 24x plus 8.8. If you just looked at that, you should be able to tell that that yes is a function. The variable x represents the number of years after 70. The variable y represents the percentage of first year college women, blah, blah, blah. Every x gives you one answer. Every input gives you one output. Okay, and that is the definition of a function. The variable x is called my independent variable because it can be assigned any value from the domain. And while yes, this domain is technically for a parabola, all real numbers, remember what x represents. It represents the years after 1970. So it wouldn't make sense to have negative numbers in there for the domain. It wouldn't make sense to have, well, anything too big. I mean, right now, if we wanted to make real sense, we wouldn't put anything bigger than 50, 51, if we watch this next year. But, the model would hold up no matter what you put in for X if you want to look into the future. So the variable Y would then be called the dependent variable because it depends on what you put in for X, right? The bigger X you put in, the bigger Y you're going to get. Okay. And we have not seen every set of ordered pairs defines a function. Similarly, not all equations with variables x and y define functions. If an equation is solved for y and more than one value of y can be obtained for a given x, the equation does not define a function. Okay? So the way we determine whether an equation represents a function is to get y by itself and see how many answers I get. if I have one input. So very easily, to get y by itself here, we would just subtract x squared from both sides. This is a function because every input gives me one answer, gives me one output. As opposed to part B, where now if I subtract x squared from both sides, I have y squared is equal to negative x squared plus 4. To get y by itself, I would have to take the square root. And then when I take the square root of both sides, I get plus or minus x squared, plus or minus the square root of x squared, negative x squared plus 4, or 4 minus x squared. Either way you want to write that. This is not a function because every answer that I put in, as long as it works, gives me two outputs. Right? Every value that comes out of the radical, I get a plus and a minus. So this is not a function. Let's try our checkpoint. I think you can tell these are pretty similar. So subtract 2x from both sides. This would be a function because once you get 1x, you are going to get 1y. And this one would not be a function. We'll write this the other way this time. Okay, square root both sides. Y is equal to plus or minus the square root of 1 minus x squared. This is not a function, okay, because of the plus and minus. Okay. All right, so let's get into function notation. Okay. If an equation in x and y gives you one and only one value for y for each value of x, if it passes that rule that we just looked at in the last problem, then it is a function, and y is a function of the variable x. So when an equation represents a function, we name it with a letter, like usually lowercase f, FGH, capital FGH. Any letter can be used to name a function, but typically, just like we usually use x and y for my independent and dependent variables, we usually use the small letter f to denote a function. Okay? So think of the domain of a function, a set of the function's inputs, and the range as the set of the function's outputs. And if you look at this little machine right there, input is represented by x and the output is represented by f of x. That's how you say that. That special notation is read f of x or f at x. Nobody really says that one. Most of the time, most people just say f of x. And what it means is the value of the function at the number x. So the input goes into this thing, whatever it is it does, whatever equation you're crunching that input through, and it spits out a number. That number is the output, which is what f of x is equal to. So let's look at our college example here. So if this defines a function of x, we're going to name that function f. So the input is going to be x. My output is f of x. And basically my equation is just the same thing. So now if we want to find f of 30, if we want to find the function evaluated at 30, all we do is we plug x into the function. So everywhere that's pink there in the description, we're going to replace the value x with 30. Now you don't have to do anything on the left, right? That's just notation. That's just telling you what you're inputting. However, on the right, we're gonna do the arithmetic, right? We're gonna square 30. We're gonna multiply it by 0.014, and then we're gonna add all those numbers together, and we get that f of 30 is equal to 14.2. And that tells you that the value of the function at 30 is 14.2. Okay, so 30 years after 1970, or in 2000, 14.2% of the college have no religious, women have no religious affiliation. Remember, that's what that equation was talking about. Okay. We used that equation to find f of 30. To find other function values like 40 or 55, you just change the input. Okay, you just plug in whatever it is you want. So if the function named f and y represents the independent variable, then you could always switch this to y and have the dependent variable. Basically, what this means is that y is the output, the independent variable. It means the same thing as f of x. So we can usually interchange those as we see fit. Okay. So let's try this. Let's input some stuff into the function. Okay. So f of 2 just means, and for all of these things, here's what this equation is saying. It's saying take whatever is inside this parenthesis, square it, multiply by 3, and add 5. Okay, so you just fill in the blank, no matter what that blank actually happens to be. Okay, so for the first one, we're going to get 2 squared plus 3 times 2 plus 5. So f of 2 gives me 4 plus 6 plus 5. So f of 2 is 15. Okay. Yeah. Not so bad. Let's try the next one. F of x plus 3. So again, my formula for f of x is x squared plus 3x plus 5. So that means that I'm going to replace every x with x plus 3 plus 3 times x plus 3 plus 5. My input is x plus 3. That's what's going into these parentheses. Okay, and now I have to simplify it. Well, x plus 3 squared is a binomial. When I square a binomial, I have to FOIL the two pieces together, and I get x squared plus, don't forget the middle term, 6x plus 9. I'm going to distribute the 3 plus 3x plus 9 plus 5. So that gives me x squared plus 9x. 9 and 9 is 18 plus 5 is 23. Okay, so f of x plus 3 turns into x squared plus 9x plus 23. And then another thing we can do is we can try to evaluate f of negative x. Let's write f of x again, x squared plus 3x plus 5. This one is important. This one we're going to use a lot to figure out things like if a function is even or odd. Okay, so this one is kind of an important thing. So we're going to input negative x into each variable just like we did with x plus 3. Okay, the difference here is that everything gets inputted into, everything gets squared, so the negative is getting squared as well as the x. So that turns into a positive x squared, but a negative 3x, and there's nothing different with the 5. So we didn't get it back to exactly where we started. My original function had a plus. Now this one has a minus. So there was a little bit of difference. We didn't get exactly the same thing. And that means something that we'll talk about in another section. All right, let's try again for our checkpoint. So f of negative 5 is going to be negative 5 squared minus 2 times negative 5, plus 7. Okay, negative 5 squared is a positive 25 plus 10 plus 7, and that gives me 42. So f of negative 5 is 42. That's part A. Part B, f of x plus 4. Similarly, we are going to square x plus 4 minus 2 times x plus 4 plus 7. X plus 4 squared gives me x squared. Don't forget the middle term, 8x plus 16 minus 2x minus 8 plus 7. x squared, so that's plus 6x and 23. And for part C, f of negative x gives me parentheses negative x squared minus 2 times negative x plus 7. And very similar to the first one is the only difference is, whoops, 2. The only difference is the sign of the middle term here. Okay, so we're able to plug anything that we want into a function and evaluate that function either at a number or at a variable or another function, in fact. So let's talk about the graphs. The graph of a function is the graph of its ordered pairs. So for example, the graph of f of 2x is a set of points x, y in the Cartesian coordinate system that satisfies the equation. So we're just going to plug in numbers and get our answers and graph our answers. Same thing for 2x plus 4. Okay. Let's graph both of these actually. So I'm going to graph them all with integers between -2 and +2. And again, like the first section, we're not going to use any fancy tricks here. We're just going to make a table. So we're going to go from -2, -1, 0, 1, and 2. So plugging them into 2x would give me 2 times -2, which is -4. 2 times -1, which is -2. 2 times 0, right? We're just plugging in for x. 2 times 1, and 2 times 2. Okay, and then I would graph this equation, which my ordered pairs would be -2, -4, -1, -2, 0, 0, 2, and 4 to get my line, and let's keep it going, kind of like that. Okay. So the next one, g of x, is 2x plus 4. Okay, so now if I make a table with the same numbers, I just plug them into the different function. So now it's 2x plus 4, which would then give me a 0 for that, a 2 for that, 4 here. 1 times 2 is 2, plus 4 is 6, and 2 times 2 is 4, plus 4 is 8. Okay, so I get a similar pattern. Right? The numbers are going up by 2s, but they're just slightly different. And we can graph this as -2, 0, boom, boom, boom. So again, there is better ways to graph a line, but for now we just wanted to plug the numbers into the function and see how graphing a function works. These are both linear functions, and we'll talk about them in much more detail in section 1.4. Okay, let's graph 2 more lines. We'll do them a little bit faster here. And in fact, we already graphed 2x. So we already know what that one looks like. That just goes through this line right here. Something like that. I messed that up a little bit. And good enough. And g of x is going to be 2x minus 3. So again, if I'm going to make my table, -2, -1, 0, 1, and 2, right? What am I plugging into? I'm plugging it into the function. So g of -2 would be 2 times -2 minus 3, which is -4 minus 3, which is -7. 2 times -1 minus 3, which is -2 minus 3 is -5. 2 times 0 minus 3 is -3. 2 times 1 minus 3 is -1. And then 2 times 2 minus 3 is +1. So now I have my coordinates. -2, whoops, -2, -7, 5, 6, 7, -5, -3, -1, +1, and I get a similar set of linear functions that I didn't draw perfectly, but you get the idea. Not every graph is a function. Okay, these two were, right? These are both functions, f of x, g of x. They're named as functions. We can assume that they are functions. Okay? But not every graph in the rectangular coordinate system is a function. The definition of a function specifies no value of x can be paired with two or more different values of y. So that means that if the graph has two or more points with the same first coordinate, it's not a function. And you can tell whether a graph has the same first coordinate with something called the vertical line test. Okay, and the vertical line test is just a simple way to look at a graph and say, this graph has more than one of the same x's. So it's not a function. And you just draw a line straight up and down. If it intersects the graph in more than one point, the graph does not define a function. So, vertical line test, very simple, not a function. It failed the vertical line test. This input right here gives me two outputs, this one and this one. This input right there gives me two outputs, these two, right? It fails the vertical line test. B, that's a line. That passes the vertical line test because no matter where I draw a vertical line, right, it's never going to hit the graph more than once. C is a function, passes the vertical line test. D, not a function. It's a relation. It is an equation that I can figure out, but it is not a function. Okay, let's look at a few more from the checkpoint. Yes for A, that passes. No for B. Yes for C, although I've never seen an actual equation like that. It looks like it might be a few different pieces, but it's still a function. D is a circle. That is not a function. Again, I can write an equation for it. I can figure out what it is, but it is not a function of x. Okay, so what else? What other information can we get from a graph? So we can obtain information about a function from its graph. At the right or left of a graph, we're going to find either closed dots, open dots, or arrows. So if we have a closed dot, that indicates that the graph does not extend beyond this point and belongs on the graph. Also, when we use the interval notation, that was represented by brackets. The endpoint is included. Open dots mean the graph does not extend beyond that point, and the point does not belong to the graph. With parentheses, we use in interval notation. Means the endpoint is not included. Okay, both of these, it stops, right? It does not extend beyond this point. The graph stops. One, it stops with the point included. One, it stops without it included. And to say that the graph keeps going, it does not stop, that's when you're going to use an arrow. Okay, so that means it's going to keep going to something like infinity. So if we analyze the graph of a function, right, as I look at this function, I see it's got a whole bunch of stuff going on, but what did we just talk about? It's got a dot there and it's got a dot there, which means this function starts and stops somewhere. All right, so the human immunodeficiency virus, or HIV, infects and kills helper T cells. Because T cells stimulate the immune system to produce antibodies, the destruction disables the body's defenses against other pathogens. By counting the number of T cells that remain active in the body, the progression of HIV can be monitored, and the figure shows the graph that is used to monitor average person's progression in the disease. So let's look at this real quick, and you can see that in the red purplish part, we have asymptomatic, few to no symptoms. Then as our number of T cells goes down, we get to the symptomatic stage in the blue, and then the actual AIDS disease in the green. Okay, why does this represent a function? It represents a function because every input has one output. It passes the vertical line test. Even right here, even right there at the edges there, it's not going straight up and down. It's going to the right a little bit, right? That's all you need to define a function. So why does it represent a function? We can just say passes the vertical line test. Oof, handwriting not coming out too good. Okay, find f of 8. 8 is the input. 8 is the x value. Where is the graph at 8? There's my coordinate that has a first coordinate of 8, and it looks like the second one is 200. So f of 8 is equal to 200. For what value is f of x equal to 350? Now this is an output. Okay, looks like these are going by 200, so that's 300. That's 350. It looks like that's about right there. So f of 6 is equal to 350. Okay, and those are some things we can tell about the graph. Describe the general trend shown by the graph. Well, pretty much it's trending down. If we look at the overall where it starts, where it stops, over time, over a number of years, the average number of T cells are going to be going down if you have this disease. So we're going to use the same picture, f of 5, f of 100. Or sorry, f of x is equal to 100. Let's go back up to the graph. F of 5 is going to be, so f of 5 is 400 because x at 5, my output is 400. 100 is about there. Looks like that is f of 9 is equal to 100. So the answer to the first one is 400. The second one is 9. Okay, and then the last one was estimate the minimum average T cell count during the asymptomatic stage. Looks like the minimum for the asymptomatic stage is right there, right? That's where that transition is. So that would be 200 millimeters of blood. Okay. And that was just some things that we can tell by looking at the graph and trying to figure out some of the data that it is giving to us, some of the things that that graph is trying to actually tell us. Okay. So next, another thing that the graph can tell us is it can illustrate domain and range. So domain, again, is my first coordinate of my ordered pair, and most typically when we're looking at the graph, that's going to be my x-coordinate. In fact, it's always going to be my x-coordinate. The range is going to be your y-coordinate. So you can see that the domain is going to be the set of inputs, range is a set of outputs, and their x's and y's. And you can see that because of these solid dots, we're going to represent the domain in this particular function with brackets in between two numbers, and the range up and down in between two numbers. Okay, we just have to figure out what those numbers are. So if we look at this graph right here, this looks like a half a circle. Okay, it's got two dots on the end, which means that we're going to use square brackets. And the domain extends from -4 to +2 inclusive. And I would represent that two ways. With set builder notation, x such that -4 is less than or equal to x, which is less than or equal to 2. But what we're going to do typically is use interval notation. that the domain of this function goes from -4 to -2, including both of them because of the solid dots on the end. And the range goes from the bottom to the top. So from -1 to -4, also with square brackets. Even though there's no dot up here, the function is continuous. It doesn't stop. So that means that we can assume that the function goes through that point. Okay. So let's look at some graphs and let's pick up the domain and range. Okay. And let's stick with, we'll do both. We'll do both interval and set builder notation for these. Okay. So the first one, the domain, okay, is the x values. So if I'm going to use set builder notation, it's x such that, well, where does it start? Where does it stop? -2 is less than or equal to x, less than or equal to 1. Okay? Or in interval notation, -2 to 1. Okay? The range is a y value. So when I'm making my set, I'm going to say y such that y does something. Bottom to top, least to greatest. Where does this function start? Where does this function stop? What are the y coordinates? They are 0 and 3. With interval notation, my range is from 0 to 3. Okay. Let's stick with interval notation just because it is a slightly shorter and easier to do, and there are a lot of these. Okay, so the domain. Okay, domain, x to y. Ooh, look, we have an open circle. That means we're going to use a parenthesis because the function starts at -3 and it goes to a +2 with a bracket. X values. Where does the function start? Where does the function stop? The range is the y values. So again, it's an open circle. It starts at 1 and it goes up to 2. Right? You can write the coordinates, right? This function starts at -3, 1, and the function stops at -2, 2. Right? That's a good way to look at it sometimes. But remember, the domain is the furthest left point to the furthest right point. The range is the bottom point to the top point. And in both of these two functions, the functions stop. It's not always true in part D. Okay? But the difference with C is that it doesn't start at a point and end at a point. It does for the domain. The furthest point to the left is a bracket with -2. The furthest point to the right, however, is a 1 with a parenthesis. Now the range, the lowest point on this graph is right there. So that's a bracket with a 1 because the function is continuous at 1. Now the highest point is right here. This one doesn't have anything to do with the range. Even though it's an open circle, well, this one's a closed circle. So 2 is included in this range. Okay, and this function goes up to 5 with a bracket. Okay, here we get our first infinite, our first arrow. So where does this function start? It keeps going left. It keeps going left. So it starts at -infinity. It stops at 4 with a bracket because it's a solid dot, right? Left and right. How far right does it go? The range, where does this function start? Well, it starts at 0. Where does this function stop? It never stops because, yeah, it's going left, but it's also going up a little bit, right? Not as much as it's going left, but it's going up a little bit, which means it's going to keep going up no matter what, all right? And our last one is a little strange. That's a weirdo function. also called a step function. So my domain here is, well, look at this. It's defined, oh, it has an open circle there, but then it's closed up there. So 1, this function starts at 1, it's defined at 2, it's defined at 3, and it goes all the way to 4, but it's not defined at 4. Well, that was, and think of them, if you sort of collapse all those steps, you can see that it goes all the way from 1 to 4. There's an output. However, with the range, okay, it's not really an interval. Okay, so you wouldn't want to write this as an interval. You would write this as a roster. The range is 1, 2, and 3. Because interval means everything in between 1 and 4, like 1.5, like 2.5. Right? If you look at the range up and down, it's not defined at anything in between the integer points. Okay, so I would never use an interval to describe something that's not an interval. Let's do a couple more. Domain for this one is bracket. It goes from -2 to a +1. The range goes from 0 to 3. Here, the domain, this function starts with a parenthesis at -2, finishes at 1. The range goes from bottom to top. Looks like it's going backwards a little bit, doesn't matter. The lowest point on this graph is a -1, and it finishes at a +2 with the parenthesis. And then a step function again. My domain is from including -3, not including 0. Range is a roster. And in order, let's try to go in order, right? -3, -2, -1. All right. So let's finish with a quick talk about intercepts. Okay. The picture at the bottom illustrates how we can identify intercepts from where a function from a function's graph. All we have to do is figure out where the function crosses the x-axis, and those gives us our intercepts. And you can see it happens 3 times at -2, 0, 3, 0, and 5, 0. Those are the points which the graph crosses the x-axis. Or we can simply say that the x-intercepts are -2, 3, and 5. You have to say, you can't just say intercept though. If you're going to list the intercepts by just their number, you have to specify whether it's an x-intercept or a y-intercept. Because the y-intercept, well, they're both, 3 is a y-intercept and an x-intercept. But still, remember that the x-intercept is 0.30, while the y-intercept is 0.03. And then we can express this in function notation by writing as that f of -2 equals 0, and so on. And because of this, because the function is equal to 0 at an intercept, they're also called the zeros of a function. Okay? And those are the values for which f of x equals to 0. So important here for later is the real zeros of a function are also defined as the x-intercepts. And then to find the y-intercept, right, same idea that we just talked about with x. We see where the graph crosses the y-axis, and f of 0 equals 3, but we don't call that a 0, right? When we call numbers that the function input gives us 0, those are the zeros of the function. In bold, important, because functions pass the vertical line test, like this function does in the picture, a function can have more than one x-intercept, but at most one y-intercept. And it doesn't have to have any, but it cannot have more than one y-intercept, because if it did, it wouldn't be a function anymore. It would fail the vertical line test with the y-axis because it would cross it more than once. Okay. So that was section 1.2, the basics of functions and their graphs.